A very good morning to one and all present here. It's a great pleasure for me to welcome you all to the 11th edition of Alumni Research Talks organized by CSA BITS Pilani. CSA is the departmental SOC for the Computer Science Department, and it stands as a powerful learning platform with substantial inflow of guidance and mentorship from seniors. The association also has an open nature, allowing the convergence of computer science enthusiasts from all streams of study. CSA is noted for organizing quizzing and coding events around the year. Innovative events such as anti-coding capture the flag during the apogee as well as the alumni research talks. The first edition of ART was held in the year 2012, and after its tremendous success, it has continued as an annual event. So we are here for the final talk of the 11th edition of the ART, and the speaker is Aditi Chaudhary. She is a PhD candidate in the Language Technologies Institute of Carnegie Mellon University. She had graduated from BITS Pilani in 2015 with MSc Biological Sciences and a bachelor's in Computer Science. She has been a research intern at IISc Bangalore and at Google, and she's also worked as a software engineer at Microsoft and completed her master's from CMU. So also her research interests revolve around the development of methods and tools to extract language descriptions such as grammar rules in all languages. She has also developed an interface to explore and visualize the extracted language description across many languages. So it's an honor to have you here with us today, ma'am. I'll hand over to you.
Okay, so first of all, thank you for inviting me. It's a real pleasure to be back here, even though it's just virtually. But I'm glad I'm still getting the opportunity to share some of my insights and research with you. So let me just begin. To give a bit about today's agenda. So I'm going to talk a bit about myself for a few minutes, about my journey so far, and then I'll just straight away dive into my research goal, which is towards building language technologies for everyone. Then I'll talk more about questions regarding PhD, masters, and I think that will be more relevant to you guys. And also, like the more important question of how to get started with research. So I guess without further ado, let me get started. So let me introduce myself formally. I am 2010B1A7 748P. I am a BITS Pilani graduate. I did my dual degree course here with my MSc in Biological Sciences and a BE in Computer Science. I graduated in 2015, and between my time, I did a research internship at IISc, which was mostly around neuroscience. So my biology background helped me get that. I also did my practice school at Walmart, which was mostly about software development for their distribution center. Uh, After my graduation, I worked for 2 years at Microsoft India Development Center, where I worked on the search and technology part. Like I specifically worked on developing Bing backend technology, and there I worked for 2 years. After spending 2 years, I thought I just needed more knowledge into machine learning because you're using these technologies in my work, but I really didn't have any background in that. So I decided to pursue a master's in Carnegie Mellon University, specifically in the domain of NLP. And I'll talk a bit about my master's program also towards the end because it's a bit unique in nature because it's a research-based program. So I also transitioned from my master's into the PhD, and during this time, I also got the opportunity to do research internships at Google Research, where I explored more around how to develop these NLP in a more industrial setting also. Right. So now I'll just get started on my research goal, which is towards building language technologies for everyone. So let me first start by motivating that how complex language is. It comprises of different words which form the vocabulary. And to form a well-meaning sentence, one needs to know how to arrange them appropriately. For instance, in English, one needs to know that Anna, the subject, comes first, then the verb eating, and then the object apple. And this also entails that we know how to transform the words also appropriately. So if you're performing an action, then you need to append ing to the verb eat. And these are formally the fields in linguistics which are called as semantics, syntax, and morphology. And each of these fields are governed by some sort of grammar rules, like what defines how to arrange words, how do you transform words. And there are just a few of the fields. This is quite a big field. And these set of rules, they are not only complex within one language, but they also vary drastically across languages. So here is an example from my native tongue, which is Marathi. So seemingly all rice in English are rice, but if the rice is cooked, then it's called bhat. But if the rice is raw, it's called tandoor. There is this very fine-grained distinction between the same concept of rice in Marathi. Also, the way words are arranged are also quite different. So while apple was towards the end in English, apple here is right next to the subject Anna. And also the way words are transformed, they're also quite different. So in English, irrespective of whether the speaker is a male or a female, you still append ing. But in Marathi, if the speaker is masculine, then you add to, which is it becomes khato. And if the speaker is a female, then it becomes khate. So you have these different transformation rules based on gender also. So clearly, understanding these language systems is important for fluent language communication and understanding. But they also drive the design and development of many language technologies, like machine translation, we are translating one language to another, creating learning tools, we are trying to learn a new language, and even identifying grammar corrections and suggesting alternatives, like many of you must have used Grammarly or in your inbuilt Gmail application. And these are also important from a language preservation point of view, where linguists document the salient points of the grammar of a language. And this is especially important because you need to have a documentation of the language which lists its properties. And this is not just important for like a teaching purpose or for development technologies, but it's also important from language preservation point of view because languages, they keep on changing and sometimes they even get extinct. So language preservation is a very important application here. Right. So what is language technology? So language technology is essentially technology that enables machines to read, understand, and respond to natural language similar to how humans would. And building these technologies requires knowledge from these fields of machine learning, deep learning, NLP, linguistics, human computer interaction, computational social science, and so on. And I think each of these fields even has their own separate master's and PhD programs, which kind of highlights that these fields are so important and vast. Now, typically, natural language processing, as you might have observed in papers or in applications, they comprise of these well-defined tasks, such as part of speech tagging or dependency parsing. So part of speech tagging is a task where you're trying to identify what role a particular word is playing in that sentence. So Anna is a proper noun, eating is a verb, apple a noun, so on. And dependency parsing is telling you what relations they are playing with respect to each other. So Anna is subject of eating while apple is an object. Another example of such a core NLP task is that of named entity recognition, where the task is to identify what are the entities and what are the categories. So in this example, John loves New York. John is a person. New York is a location. And let me give you a concrete example as to why NLP often has these core NLP tasks. So when you say ask your phone to show you trains from NY to Paris, then the model or your phone inherently is performing the task of entity recognition, where it identifies that NY and Paris are locations where NY is a source and Paris is a destination. It also resolves NY to New York and potentially then goes back into the database and gives you the possible options. So to evaluate how well your machine is understanding language, NLP has defined these core NLP tasks like entity recognition, question answering, machine translation, and so on. And thanks to the advances in machine learning and deep learning today, many of these NLP tasks, which also form a core component of language technologies, they have achieved quite a high performance today. So NER has become like more than 94% accuracy, part of speech tagging more than 95%, and so on. But of course, this comes with the asterisk that this high performance has been observed only for a handful of languages, and that is primarily English. And the reason being that deep learning models are quite data hungry. That means that they need large training data to achieve such high task performance. So here is a plot highlighting the same point as to why most language technologies today are English-centric. So each circle on this plot is one language, and the size of that circle denotes the number of speakers it has. And on the x-axis, you have the number of resources, an approximate idea as to number of resources each language has so far for training these models. So as you can see, excluding English, majority of the top 10 languages spoken in the world today are on the left half of the graph, which means that they don't even have half the resources which English enjoys. So basically, there are few languages which have many resources, and thus they benefit the most from deep learning methods, and of course, thereby have better language technologies. On the other hand, there are many more languages which have very few resources, and thus they often get ignored in this development. But if you notice the number of speakers each of these language has, so English currently is serving 1.3 billion speakers, but the rest of the languages, they have almost 3.5 billion speakers together. So clearly, a large percentage of the population is still not served. And language technologies not only are like ubiquitous, but they also become quite necessary. So as we saw in this pandemic, where information about the virus needed to be propagated to everyone in the world quickly. So essentially, you needed good machine translation systems to translate the set of like instructions very precisely and also very quickly. These technologies have also been instrumental in rebuilding refugee lives by creating education materials and even helping with accessibility. So I think none of you can now imagine a world where you don't have access to any smart devices. And that is this has also increased accessibility for people with special needs. So clearly, language technologies have become a good necessity today. So, given this high level motivation, I'll now present some of my research. Specifically, I'll discuss briefly approaches to improve NLP tasks for under resourced languages. I'll also discuss how to leverage these methods for automatically deriving linguistic insights from natural text and like show its utility in some human and machine centric application. In the interest of time, I'll just present two of these works in detail. So, given that existing state-of-the-art models have been developed for high-resource languages, we want to quickly adapt them to any new language. And many of these are under-resourced. So by under-resourced, I mean that they have insufficient quality or quantity of label data or just any data in that language. And this is a nice plot from the Endangered Languages Project, which highlights the extent of such languages. So this is a nice plot for two reasons. First, you can see that there are so many languages, like there are almost 7,000 plus languages in the world today. And secondly, many of them are orange or red colored, which means that these languages are severely endangered or they're close to getting extinct. This also means that we need to act urgently to save them from getting extinct. Because if we don't build technologies for them, then it slowly goes out of use and it might get extinct much sooner. So, given that there are so many languages, like it seems a very daunting task, but the good thing is that languages are related. They belong to these language families and they of which often share like grammar properties and even vocabulary. So for example, consider English and German. They both belong to the Indo-European language family. And there are just two sentences in that languages. And even by just looking at the German example, you can see that it's quite similar to English. And because there are so many overlaps across these languages, the neural network models, which also rely a lot on these surface level features, they benefit a lot. So if we have access to data or models from a high resource language like English, we can easily like build models and tools even in German. But if we consider another language pair, say Hindi and Bengali, which also belong to the same language family of Indo-Aryan, and here now looking at the sentences, you can see that there is like no overlap. And the reason being that they are written in different scripts. So, but we do know that Hindi and Bengali, they are like quite similar, but because they don't share the script, then how do we like encode the similarity? So we can leverage the fact that we do know Hindi and Bengali, they share sounds. So if we now represent the text using a phonetic alphabet, we can immediately see the similarity being apparent. So essentially here the representation is shown in an international phonetic alphabet or IPA for short. An IPA basically encodes or tells you how a particular word or how a particular syllable is pronounced. So it's representing, it's a universal alphabet, so you can represent potentially any language in terms of this representation. So now that we have the phonetic representation of these languages, we can now see that the similarity it becomes even more apparent. So now how to leverage the similarity through a neural network model? We can use word embeddings. So word embeddings, as you know, they are like continuous vectors which help capture properties of a language and have also shown to improve performance of NLP models. And one such popular algorithm, which I'm sure most of you must know, is the skip-gram objective function proposed by Mikolov and others, where essentially given a sentence, now you have to train or learn a representation for the word flying. So basically, you project the vector for flying into a continuous space, and you train it to predict the surrounding words like bird, park in this example. And the main premise behind this approach is that words which occur in similar context will be closer in the representation space. So potentially flying, walking should be similar because they're both verbs. So it tries to capture both syntax and semantic similarity. However, a major issue with this approach is that it doesn't handle words which it hasn't seen before. So let's say we have learned a representation for flying, but what if fly was never observed during training? But we know fly and flying should be same, but the model doesn't know that because it has not seen fly. So can we model something other than words? Yes, so we could model subwords. So subwords are basically, you can say, subunits of the word itself. And previous work have modeled subword in the form of characters and morphemes, along with the whole word itself. Let me just illustrate what I mean. So if we take the same example, so now we can decompose flying into its character n-grams. So we have one vector for FLY, one for LYI, one for ING. And now the representation for flying will just be a sum of all of these individual n-grams. And now, even if the model didn't observe fly in training, it has still learned a representation for it. But what about the word flew? So even if we decompose into its n-grams, flew doesn't have matching n-grams with flying. But we do know that flew is basically the past tense or the past participle form of the verb fly. So now, along with character n-grams, you can also decompose the word into its linguistic units. So we have one representation for its lemma, which is fly, one for its morphological units, which is verb and past participle. And we also have representations for n-grams. So now a word is basically a sum of all of these different units. So now that we know a way to encode subwords also, can we use it for transfer learning? What I mean by that is, can we now make use of this information to also bring together the Hindi word for flying close to the Bengali word for flying? So how do we do that? So we propose using linguistically inspired subwords. So consider the earlier Hindi example with its phonetic representation. So for learning the representation of udne, we propose decomposing the words into three categories. Graphemes. So graphemes is the original word itself. Morphemes, as I showed before, it's the decomposition into its grammar properties. So we have its lemma and the morphological tags. And then you also have its phonemes. So phonemes is the phonetic representation of the same word. So now we basically modify the skip-gram objective to include these different linguistic units and learn the representation of the word as before. So if you note, there's like a small difference here. So along with encoding each unit with one vector, we're also taking an average of all units as opposed to taking a sum as the previous works did. So taking a sum is a problem because some units might have more number of n-grams, or some words may have more number of morphological tags. And this might bias the model to, build better representations for too small or too big words. So by averaging out this, you're trying to learn or treat all words equally. So now that we have a way to train embeddings, now how do we train them cross-lingually so that the similarity between the two languages is encoded? So we experiment with different kinds of approaches in our paper, but I'll just present one of them here in the interest of time. So essentially what we do is we take the monolingual data, that is the data in that language, and we decompose the data into its linguistic properties. So in this case, our high resource language is Hindi and Bengali is our under resourced language. So you decompose both the text in both languages into its graphemes, phonemes, and morphemes. And then you combine this data in a clever fashion, and you basically apply the subword objective on top of that. So this basically results in your cross-lingual word embeddings. And basically, you can just plug them into any downstream model, such as a model for NER or a model for MT. And the hope is that because we have trained these models across two languages which are hopefully similar, the hope is that the cross-lingual embeddings will help the model leverage data from both the high resource and the low resource language. So we are hoping that through the subword decomposition, we are trying to make the words in Hindi closer to the words in Bengali and vice versa. And because these embeddings are trained offline, they can directly be used for any downstream task. So you need not like train them each and every time. So now we evaluate the quality of the learned embeddings on a downstream task such as named entity recognition, wherein basically the task is to identify and classify named entities into person, organization, etc. So here we have an example where Pratibha is the person and Bharat is here location. So we experiment on two language pairs. So these belong to different language families. So Bengali is a low resource language for Indo-Aryan, and Uyghur is another low resource language from the Turkic language family. It's spoken around parts of China. And in both cases, we also add a related high resource language. So for Bengali, we are using Hindi, and for Uyghur, we are using Turkish. And note that in both the language pairs, the high resource language and the under resource language, they have no lexical overlap. So even in the case of Turkish and Uyghur, they don't share any scripts. And as you can see from this plot, which is basically showing the number of training examples we have for NER task, you can see that the under-resourced languages of Uyghur and Bengali have like much fewer label data as compared to Turkish and Hindi. So clearly, these are under-resourced settings. So now we compare, as is the norm, you compare your approach with some existing baselines. So in this case, we have used baselines of multi-CCA and cheap translation. So both of these baselines basically make use of bilingual resources. By bilingual resources, I mean resources which have like parallel corpus available, or they have some dictionary information. And basically what both of these approaches are doing is that they make use of these bilingual dictionaries to basically align the language space of the high resource and the low resource language. On the other hand, we also compare against different variants of our model where we are experimenting with different combinations. And note that none of our model variants require the use of bilingual resources. And often bilingual resources for like very under-resourced settings might not be easily available, or in fact, they may not be of great quality. So that is one assumption we make, that we're not using any bilingual resources. So now going to the plot, on the x-axis, you have the language pairs, and on the y-axis, we have the F1 score. So F1 score is basically a metric to measure the performance of NER, and the higher the better. So first, we can see that when we use subword information, or rather when we use any of our model variants, it outperforms the baselines for both the languages. And secondly, we find that, and especially when we're using the subword unit of phonemes, we see the best performance. And this is reasonable because both Bengali and Uyghur are written in different scripts than the related languages, and phonemic similarity helps bridge the gap. And if you also think about it, like when you say New York in Hindi, or when you say New York in English, the entities tend to sound very similar. So they don't change how they are pronounced significantly. So even if the languages may not be that related, but for the task of NER, using phonemes will definitely be more helpful. And the promising part here is that because we're not using any bilingual resources, that means that you can still get away with like subword information for like very under-resourced settings. So even if you forget everything about this plot, I think you should remember the two main takeaways. One is that related languages help, like they help a lot. And two, designing linguistically inspired methods can help you leverage the relatedness more effectively. So, is this the only way to add support for a new language? Well, no. There are several ways, and here is a nice flowchart which I've borrowed from my advisor's course slides. And that is basically demonstrates the different paths one can take based on what kind of data or computational resources one has at hand. I've also explored some of them in my work. So, for instance, if you have some label data in your target language, like we did in the previous example, and we're not constrained by computational resources, then potentially we could use supervised learning, that is, we train on the label data itself, or we can even use cross-lingual learning, where we are learning from a related language like Hindi or Turkish in that case. If you don't have any label data, you could do some data labeling to make that fast. We can potentially use active learning. So for instance, what is active learning? So active learning is basically a family of machine learning methods wherein it helps to intelligently select what data to label for best model performance. So ideally, if we have enough budget and time, we would want humans to come in and label each data point for us for any language. But that is, of course, not the case because it's very time consuming and also expensive. So what active learning does is active learning tells you like, okay, take this subset of data, and if you annotate this subset, it will give you the best model performance. So it's an intelligent data selection method. And the way it's implemented, it's an iterative process where given some initial machine learning model and some unlabeled data, the active learning basically has a bunch of strategies which you can apply on the unlabeled data to select what data to label. You present that data to some experts. The experts then label it. So in this case, they have labeled the part of speech for the unlabeled data. The labeled data is then put back into the labeled pool and the model is trained again. So essentially, this cycle continues until you have either exhausted all of your unlabeled data or you have achieved a certain level of accuracy. And to further improve this active learning, we can also like bootstrap it with transfer learning approaches, because we just saw that transfer learning like really helps for under-resourced case. So basically, I've explored two directions in this work, and I highly encourage you to check this out because active learning is often ignored, but it has like very neat tricks to like select what data to label. Right. So now we have seen one pathway. Now, what if, let's say, you don't have access to any native speakers? So in that case, potentially you could do a zero-shot adaptation. And what I mean by that is that we can basically pre-train a large neural network model on data from multiple languages. Like in this case, we are using Hindi, English, and Spanish. And you can pre-train these large, deep networks, maybe as you might have seen BERT or XLM, so on, and you can directly apply them on any low resource or any language, and hopefully the target language benefits from these high resource languages. And typically the way these models are trained is given a sentence, you mask out some words, like basically you make sure that the model doesn't see that word, and then you basically make the model predict that masked word. So it's sort of like a fill in the blank, like how a human would do. And such an objective essentially forces the model to understand what context in which the word should appear. And this essentially helps the model to learn better word representations. But we also hypothesize that by requiring a model to predict the word in that language always, how will it learn to make other synonyms, like let's say the Hindi word for food khana or the Spanish word for food comida, also closer to the English word food? So we explored this a bit in my internship, where basically we proposed an approach where along with predicting the original masked word, we also make the model predict its cross-lingual synonym. So in this case, if we mask out food, we want the model to also predict the Hindi word for food or the Greek
Excuse
word.
me, ma'am.
Sorry, yeah,
Yeah, there have been two questions on the chat. Oh,
sure. So I can stop here.
right.
Can
Should
you
I
read
read
that
them
out?
out or?
Yeah, I cannot see the screen, so it would be better if you read
Right,
them
right.
out.
So the first of it was, will Sanskrit have its NLP presence as strong as English?
Okay, so I think there has been a lot of exciting work going on in Sanskrit, And I think Triple IT Hyderabad has done a lot of like data annotation. So it has seen a lot of progress in the past few years. But I think one main reason why it might not see that much advances as what English has been seen, probably because English is spoken a lot and Sanskrit is still not spoken to that extent. But that being said, from a research point of view, and because Sanskrit has so much data and there are a lot of Indian languages which stem from Sanskrit, so potentially research on Sanskrit could definitely help with in advancing research on other Indian languages.
Right. There's also another. Can any
Mhm.
self-supervised and or unsupervised model techniques be used for language tasks?
Oh yes, definitely, definitely. So I think so. This example which I'm showing right now, this is basically an example of self-supervised, or maybe you can say unsupervised task, because this approach is basically just using information from the text. You don't have any label data available, but in fact, by masking out words, you are creating label data of some sort. So this is essentially an example of unsupervised training objective. And this is not just the only way. You can cleverly make use of unsupervised objectives for like different tasks too. So yeah, there's like a whole bunch of research going on in this area, and based on what your end task is, like if you're like in this case, the end goal is to learn better language representations. But if your end goal is, let's say, improving NER, so there are like specific methods to also like do unsupervised training for NER.
Right. You may continue, ma'am. I'll notify you if any other question pop
Sure,
up.
sure, that would be great. Right. So basically, yeah. So here we're doing a multilingual adaptation, and as we just talked about, it's an unsupervised method. So given some, you just need like raw sentences in that language, and you can still train this highly complex model. And like this is a very neat architecture, and I'm not going into too much detail right now because it will take another 1 hour. But the main takeaway from this is that basically you are making the model like understand or rather learn in what context word is appearing, and not just the same word but also its cross-lingual synonym, so that the model tries to learn better representations across different languages. And the advantage of like such pre-training approaches is that the resulting representations, as we saw in the example before, we can just plug them into any downstream task like NER, MT, and you can get like a big performance boost. So I highly encourage you to check out this in the paper for more details. Right. So now we saw some ways to improve performance on under-resourced languages. So now let's see how we can apply it to build some tangible application. So I think you'll enjoy this part more. So there is a need for good learning materials and tools for language learning specifically. And this is a report from Duolingo in 2020, which basically highlights the reasons why people are learning Spanish today. And you can see that there are a variety of reasons. Some of them are learning for their school curriculum, some for tourism, some just for like teasing your brain. So there are like multiple reasons as to why people are choosing to learn languages. Additionally, the more important application is that there is need to revitalize endangered languages. So this is a report from UNESCO, which basically identifies that there are 191 endangered languages in India today. And the main reason for the languages getting endangered is the primacy given to English and Hindi as the medium of instruction in schools. This often ignores the local and native languages. So, what they point out is that at least 6 years of instruction in the mother tongue is needed to reduce this learning gap for minority speakers. So, clearly, there is a need for good learning materials and tools. But that being said, curating learning content manually can get very expensive. And oftentimes it's difficult to find subject experts. So, for instance, there are so many tribal languages too. So you cannot simply like get on the phone with them and like ask them to like curate material. It is expensive, and it's also like the experts might not be easily accessible. So in this work, we study if we can automate some of the processes of content creation. So specifically, we focus on semantic subdivisions in vocabulary acquisition. So I know there are a lot of heavy terms. I'll just break it down. So basically, vocabulary acquisition refers to learning words in a new language, which is called L2, from a known language, L1. So for example, we are learning Spanish from English. So here, English being the known language is called L1, and Spanish being the new language is called L2. So there are some words such as linguistics in English which have like a single translation in Spanish. So linguistics is linguistica. And if you simply memorize this word, then you're done. Then there are words like bank, and bank has two senses in English. So bank can be used as a financial institution, or bank can also be used as a river edge. And interestingly, in Spanish, each of these senses has a separate translation. So banco means financial institution and orilla means river edge. So there is still a one-on-one mapping, and maybe you can still get away with memorizing these one-on-one mappings. Then there is another category of words where the same sense in English has distinct translations in Spanish. So, for example, all walls are wall in English, but in Spanish, some walls are called pared and some walls are called muro. And we refer to these words as semantic subdivisions. And such fine grained lexical distinctions arise because languages carve up their semantic space differently. So, if you recall, in introduction, I also gave the example of cooked rice versus raw rice. This is very similar to that, where the same concept in English is now subdivided into two concepts. So, in this work, we focus on helping learners understand such fine-grained distinctions because we believe this might be a bit more challenging. As if, let's say, you're an English speaker and you don't know Spanish, then possibly you're not aware that there's such a semantic subdivision in another language. So, you want to focus on such category of words. And right, so based on the four images, can you now guess like how the semantic space is divided for Spanish? So I'll just give the answer. So basically, if you look closely, the top two images are walls which are outside. So there may be a garden wall or a city wall, and they're therefore called muro. While the bottom two images, they're showing walls which are inside a house, and therefore they are called pared. There is this fine-grained distinction between outside walls and inside walls. So now you know two Spanish words. Right. So now first we attempt to identify such words which have distinct lexical distinctions in L2 based on L1. And we do this automatically by starting with a parallel corpus, in this case English to Spanish. So by parallel corpus, what I mean is that you have a bunch of sentences in English and you also have the sentence level translations in the Spanish. So but we only have the sentence level translations. So the first step we do is we want to align the respective words in each languages. And for that, we use an automatic word aligner. And there are like very good algorithms for doing this. So we just use the best which is available online. And we then apply a set of filtration steps, which gives us a list of fine-grained divisions like this. So on the left, you have the English word. And on the right, you have the possible Spanish lexical choices. And the way we like apply filtration steps is that we present very different filters. Like we filter on frequency, we filter on entropy, we also filter on word sense. But we discussed this in detail in the paper, but I'll just go through one of the key filters, which is filter on word sense. So essentially, in this filter, we remove word pairs where the English word has different English word senses for its corresponding Spanish choices. So, for example, if when we looked at the example of bank, we found that bank in English has two senses, and each of the sense also has a different translation. So, a word sense disambiguation model basically like tries to identify the different word senses. So, we essentially try to identify such pairs where each of the different word sense also has a different translation. And once we identify them, we basically remove them because we are more interested in the challenging set of words where even a word sense disambiguation model is not able to distinguish, which are the more fine-grained distinctions. So now that we have identified the learning content, we then learn a model for lexical selection, from which we basically extract human and machine readable tools. So we learn a model for each source English word, and construct the training data from a parallel corpus. So for example, let's say we're learning the model for wall, and for the training data, we have basically an English sentence as the input, which contains the word that we are learning. And the model is required to predict the correct Spanish word for that sentence. So, for example, the first input example is saying that for weeks we have waited outside the walls of Paris for your arrival. So, here it's referring to the muro. So, we basically have such kind of a training data, and essentially the task becomes a binary classification where the model is required to select the correct label based on the source English sentence. So now that we have training data, we can extract features for that. So here I'm just illustrating on a very high level how we do the feature extraction. For example, for the English sentence containing the word wall, we can extract features like looking at words which occur in the neighborhood. So for example, we have words like walk, city, foot, and we can extract some sort of grammar properties of them, word sense features, lemma, etc. So I just won't go into details. But essentially what we're doing is we're looking at the neighborhood of the word wall, and we're extracting features which are based on its lexical or semantic nature, and we try to put them into our model. So since our goal is to extract rules which are human readable, we use a model that is conducive to interpretation such as a linear SVM. So a linear SVM, as you know, it's a linear classification method, and it's interpretable because it exactly tells you what features it's giving importance to when classifying. So in this case, let's say here are some features which the model found important, and here are the model weights it has assigned to each of the features. So essentially, we can extract the top n features for each label. So as you see here, for the Spanish translation pared, we have features like hang wall, picture wall. This kind of suggests that it's referring to a wall where we hang pictures. So possibly the wall is inside. Similarly, for muro, we have features like walk, city, outside, which kind of means that it's referring to walls which are outside, like a city wall maybe. So based on the linear SVM, we can identify such important features for each class, and we can construct a human readable rules from these features. I'll show them to you in a few slides. So now we have a model, let's evaluate it. So we first compare our model with a frequency baseline, which essentially selects the most frequent label in the corpus. And I highly recommend that you always compare against this baseline because it will tell you also like how balanced or unbalanced your underlying data is. Next, we compare with the decision trees, which is also an interpretable model. And across the two languages, English to Spanish and English to Greek, we find that linear SVM performs the best. We also compare against BERT, which is a more complex neural network model. And we find that, of course, BERT outperforms the SVM. But if you closely look, BERT, despite being such a high complex neural network model, is only slightly outperforming the simple models of linear SVM and decision trees. And this kind of highlights that the underlying task of like this fine-grained distinctions is still quite hard for BERT. And next we find that BERT, like because it's a very deep model, it's not easy to uncover like what features the model is looking at when making a decision. So maybe you can like in the future, you can apply better interpretation methods to these complex models. And in fact, this could be a research project when you guys, which you could pick up. But for now, linear SVM works fine and we like go with that. So because our main motivation is to check like how well this learning content is helpful in learning process, we conduct a human learning study for people who are not familiar with Spanish and want to learn from English. So we basically present learners with this interface where on the left, you have the English sentence containing the word to be learned, and you also give them the Spanish translation. They then have to select, like looking at the English sentence, they have to select the most appropriate choice and also mark how confident they are in the selection. So note they're only shown the English sentence with the word, and they're just asked to select which is the correct option. And we basically want to check whether the learner is able to distinguish when to use one translation over the other. So we first set up a control study, like that's what you do in a human learning setup. So in the control setup, we don't present learners with our extracted rules. We just provide them with the correct answer. So basically, once they identify a particular or they select a particular option, we just tell them whether that answer was correct or not. So we kind of expect that learners will likely start with a chance accuracy, in this case 50-50, but with the feedback that, okay, this answer is correct or incorrect, they may grasp the patterns and may improve. In the treatment study, we do show them descriptions of the features we extract for each translation. So if you recall, from the linear SVM, we extracted the top n features for each label. So we now present them as rules here. So essentially, we are showing the context under which one label should be chosen. And they can review these before they start and also can access them during the exercise as well. And along with showing the correct answer, now we also highlight the most relevant feature in each example. So this kind of acts like a hint for the learner to help them understand why a particular translation was correct. So like in this case, the correct answer was Muro. And we thought that the correct answer, or rather the model thought the correct answer was Muro because there was tone in the source sentence. So possibly this is kind of drawing the learner's attention that they should look at these words because these are kind of indicative of when Muro or Parath should be used. So now, how do you compute learner accuracy? So accuracy, you cannot, specifically in a learner setup, you cannot directly compare against the goal labels because in learner, like when you're doing a human study, you have to account for multiple sources of variability. For instance, each learner could be different. They have different learning abilities. Because we present them with multiple words, some words could be difficult and some could be very easy. Also, the way examples are presented to the learner could also influence their learning. So basically, these are like some sources of variability which we need to account for. So basically, we on top of our learner accuracy, we apply a mixed effect models, which in short is essentially capturing two kinds of effects, random effect and fixed effects. So random effects is basically modeling the variables which are responsible for this random variation, like task, order, etc. And fixed effects, which is modeling the variables of our interest. In this case, we are checking whether presence of rules is helping the learner or not. And it's just the formal equation for that is very similar to your linear regression model, but you have now a fixed effect coefficient and a random effect coefficient. The fixed effect coefficient basically informs about the gain with access to rules, and the intercept here is informing about the accuracy without access to rules. So I encourage you to check more about these mixed effect models because they are quite interesting. So we conduct the study for two languages, learning Spanish from English and learning Greek from English. We employ 7 learners for Spanish and 9 from Greek, and we experiment with 9 and 10 words respectively. So here we present the aggregated results comparing the learner accuracy across the number of examples attempted. So we can see that for Spanish and Greek, learners, when they have access to rules, that is the line in red, they have much higher accuracy than learners without. Further, we can see that learners learn faster with rules. For instance, for Greek, we can see that only after seeing more than 100 examples are learners without the access to rule able to match those with rules. So you can see that the line in red, even with just 10 examples, you have a high accuracy, but the yellow line only matches the red line after 100 examples. So clearly, the rules that we are extracting automatically and showing them is helping learners not only learn better, but also faster. So we saw some aggregated results before, but of course, not all words have the same performance. So on the y-axis, we plot the beta coefficient, which basically is measuring the accuracy gain obtained with learners when they had access to rules. And on the x-axis, we plot learner accuracy when they didn't have access to rules. And we can see a negative correlation, which essentially means that rules especially help more for words on which learners perform the worst. So for instance, words such as wall, farmer, and oil were especially difficult, or rather they had much more fine-grained lexical distinctions. And the presence of rules helped these learners with these difficult words. And this is encouraging as we exactly want to do this. We want to help learners when they are stuck in their learning process. Yeah. Next, we also see that rules help more for words on which the lexical model performed well. So if it is a positive correlation, so this kind of means that the more improvement you do on your underlying model, the better quality of rules you extract. So which also means that there's a lot of scope for improvement, and improvements to lexical models will also improve the quality of rules further. So we have used these automatically derived semantic subdivisions not only for language learning, where we basically use it to like extract clues or hints to help learners understand, but we also are like using this data set to apply on machine translation models to evaluate whether the machine translation models are looking at the correct context when they're translating, and if they're not, we try to like make the model look at the correct context. So essentially you can now use the data set not only for human application but also for like machine applications. So we have seen today how we can build language technology from NLP tools and also apply them to actually help people. And I'm revisiting this slide which I showed earlier to highlight the importance of each field in building language technologies. So today I specifically chose these two pieces of work as they require knowledge from all the fields essentially. For example, in the first work of subword training, we relied on linguistic knowledge to understand like how languages are related, whether they're related through their script or through their pronunciations and so on. So it required linguistics knowledge. In the second piece of work where we designed language learning game, this it entails knowledge from human computer interaction, because that field essentially deals with how humans interact with machines. And of course, machine learning and deep learning are core to all the methods here. And often people have this impression that machine learning can solve everything. I tend to think of ML as like providing you with the right set of tools, but having knowledge of these auxiliary fields is very crucial for building better models. And you will often see when reading papers, a lot of the approaches are based heavily on linguistic intuitions and in fact can help you better design models. So now I'll go on to the more interesting part for I think you guys. And these are some of the questions like which I have been asked over the years. So I'll just compile them for like talking points. So why a PhD over masters? Right. So this is like it has like no right answer, but this is like my take on this. So essentially, PhD gives you the opportunity to explore a field in greater depth, while in MS you focus on breadth. So an instance being like maybe in masters, you could do projects stemming from text. You could do projects involving vision problems or even involving speech. So you focus on different areas. In PhD, like once you have explored the different options, you pick one topic and then you explore it to the very depth of it. So sort of you become an expert in your topic. And not only do you become an expert, but it also gives you the skill set to identify what problems to tackle, how to identify a new problem, how to propose solution. You kind of develop this intuition as to like what will work, what won't work. So you end up developing proof of concepts, which people can then use it to help their applications. And also, like a perk being that you get sponsored travel to certain locations because you get to present your work at conferences, which is often funded by your university. So that's like a big perk. Okay, next is PhD only theoretical? So here I would say it depends, and a strong theoretical foundation is always necessary. So you need like, especially in the field of ML and AI, you need to have your mathematical foundations pretty strong. But that does not mean that you need to do your PhD only focused on say optimization or like on very theoretical things. You can use this knowledge to be even more application oriented, and many fields like many topics in NLP today are quite application heavy. So it's not compulsory that PhD always is theoretical. It can also be very application heavy. Right. How to know which research area I'm interested in? This is like a very common question, and I think it's only there's like no good way. Only way is to get your hands dirty. Like you start with a project, maybe even a course project. You do it, you explore it, you see if you like it, and you take from there. You read a lot, you read papers, you can read blogs to see like what area you find exciting. Talk to people, talking always helps. You get to learn from people's experience. Don't be afraid to try different areas. It helps you explore, and you might even go like interdisciplinary. Like you might combine NLP with biology, you might combine NLP with economics. So it's like there's like no upper bound as to where you can go with this. Okay, what if I'm not sure about PhD but want to try research? So you start with a project, maybe even a course project. Do research internships. I highly encourage you to like do internships. It's a very good opportunity to like see firsthand what or how research is done. You can even do a research based MS. So this is exactly what I did. So CMU LTI basically offers this MLT program. MLT is Masters of Language Technologies. And this program basically is a very nice combination of both research and coursework. So essentially, half the time you spend doing research projects with professors, with PhD students. You also like get to learn more. You like also do coursework. So it's like a good combination and gives you a good flavor of what a PhD would look like. And if you like it, you can continue in the PhD program. But let's say if you don't see yourself being fitting into the PhD, then you can graduate in 2 years and get a job in any industry location as well. So this is a very, very good program because it gives you an exact idea of what research would look like. So you're not diving like blind into the PhD program. And also the research based master's program, it helps you like even explore the breadth. So you can work on, let's say, speech in your master's, but let's say on in your PhD you want to focus on vision, so it's completely fine. So MLT is essentially designed to help you explore what you like. Okay, what if I'm sure I don't want to do PhD? Do I still do research now? Well, yes, a big yes, because research experience always helps, even for your master's application. Like, even if you, I think, even don't go for master's, a research experience today is highly valuable. So, I highly encourage you to look for opportunities where you can do research and start doing it. Okay, so now how to get started with research? So attend talks first of all, like because it gives you an exact idea as to what is going on in the world today. Often you're like busy with your coursework and assignments and you get bogged down, but the world is also progressing very fast. So if you attend talks, you get a quick summary of what is going on. Meet people, and this also helps with networking. Meet people, talk to them, and BITS has such an amazing alumni network. Utilize it. You have so many alumni working in so many different fields, in different countries, in different locations, so you can like easily learn from their experiences, and like they tell you exactly like what helped them in the journey, what didn't help them. So please make like good utilization of that. Read technical blogs. So you even, I know like reading papers can get overwhelming and it takes practice, but there are these technical blogs which are like short summaries of the papers, and they are written in a more friendly manner, so you can get to know the latest developments in the field in like maybe 5 minutes. Of course, I do encourage reading papers because ultimately that gives you the a depth inside like the research project itself. But technical blogs are a good way to start doing it. So like for example, this is a very nice blog by Sebastian Tudor. He basically writes about like every few months he writes about what are the advances in NLP, what are the challenges people have seen so far, what are the interesting directions going forward, and these directions might even inspire your own course projects. So just read blogs whenever you can, and it just takes 10 minutes. So it's not a very heavy thing to do. And of course, get started. Don't procrastinate a thing. Use your course projects, your SOPs to get acquainted with research. So even if your research project doesn't end up with a paper publication, I think that experience really helps. And especially I think in the field of ML and deep learning, you can only like you have theory for like good background, but implementation is a whole different thing. So unless you actually start implementing something, you don't really know what works, why it works, or rather how to get things working. So just get started. And there are like today so many research projects, and there are like good toolkits available online. So yeah, just get started. I think that's the key here. Also, do research internships. So, for instance, many institutes today offered internships, like even universities. So, for example, CMU LTI also offers summer internships, and this is basically open for everyone. And the applications start in early October. So, apply early. And this is like a 2 or 3, I think 3 months internship where you get to work with a professor directly. So I think so. This was not. I think this program just started like 2 years back. So it has been really, really successful. You get an immediate access to a university network. You get access to professors, to PhD students. It helps you build networking. So it really, really helps. Also, keep on checking university websites because they usually advertise internship opportunities. So be proactive and do that. And also, an advantage of like working directly with university professors is that it might help you get good letter of recommendations. So if you are planning to apply for, say, a master's or a PhD program, a good letter of recommendation carries a lot of weight, like a lot. So I cannot emphasize how important letter of recommendation is. So if you get opportunities to do research internship with professors, then they can get you good LORs too. Also, you can reach out to individual professors, PhD students. They are quite open to like mentoring, to like talking with you is fine. But like don't just spam them, like come up with some agenda to talk to them. And like if you're like apprehensive of reaching out to professors directly, reach out to their students. Like PhD students are super helpful. They can like give you good guidance too. And often I have seen PhD students also mentoring undergrads. So yeah, like just reach out, get some information, because having information at your hand is really important. And also after your graduation, like there are also opportunities to get into research. So I know like Google and Microsoft have these pre-doctoral programs where typically you do like 1 to 2 years of research, and that gives you an exact idea as to whether you really want to go into a PhD program or not. So I think most of these are funded. So it's a very good opportunity even after your undergrad, whether you want to like try research or not. So I guess I'm just going to wrap up here. And here is a way to like communicate to me. You can write me an email, and hopefully I'll respond to you in time. But yeah, thank you for like listening to me, and I'm open to any questions from you guys. Should I like stop sharing?
Yeah, you can stop sharing, and in the Emmet you can see the list of questions a few people have asked.
Yeah, let me just try to open it. See if I can close this. Maybe I'll just keep it now. Yeah. Okay. Is there a way to navigate this? Like, is there an order to which these questions have been asked?
Yes, actually, the bottom ones were the order is that the top ones are the most recent ones. So I guess you can go from bottom to top.
Okay, I'll go from bottom to top. Okay. So the first question I'll read out loud is, for having better translation, can multimodal knowledge graphs help? That's a interesting observation, and yes, definitely, definitely. I think there has been some work which has, I think there's been a lot of work actually on exploring signals from different modalities like vision and audio. And I think there is a lot of scope because sometimes like when you just see text, you don't have any background knowledge, but when you see an image, you get a story out of it. So I think there's a lot of scope as to how you can combine both knowledge from vision and language. It's not very straightforward as to how to do it, but there are people who are exploring this, and I think it has a lot of potential going forward. Okay, next. Is BERT less scalable than SVM? So it depends. So BERT because it's a very deep neural network, and to get good results you need to like train it on a lot of data. So in that aspects, if you are constrained by some computational resources, like you need these GPUs to like train GPUs, even TPUs. So SVM is a very computationally efficient method and it works very quickly. That being said, so on like scalability aspect, definitely SVM is more computationally cheap to work with, but it also depends on the application because like SVM or especially linear SVM handles only linear spaces, but BERT being highly complex can also like do much better because it can handle non-linearities in a better fashion. I think there's a follow up from there. How to interpret BERT versus SVM? I think that's the question which people have been trying to answer. Like because BERT, like SVM, especially linear SVM, because it's linear, you can easily get to know what features are ranked higher for solving a particular task or label. Whereas BERT, because it is so deep, it has like I think 12 layers, and you also have non-linearities in them. That makes it very difficult to like uncover like exactly what are the features which the model is looking at. That being said, there are mechanisms of inspecting these deep networks, and I think if you're familiar with it, there are like attention mechanisms which like kind of tell you explicitly or implicitly that what the model is looking at. But again, interpreting that itself is a challenge. So, short answer is it's difficult to interpret BERT, but it's not impossible. And there has been a lot of good research going on in that direction, like how to interpret these models. Can more generative models be used like variational autoencoders for having a representation of features or lexical units? So I guess variational autoencoders, like they basically try to reconstruct the original space, and they also like work with trying to minimize the distribution. They have this latent representation of units. So I think they have been used to some extent, but I think empirically I have not seen them performing better for like all tasks. Various encoders have been like useful in some structured representation tasks, like where you need to understand structure of language. But I think sometimes it gets very tricky to also train these VAEs. So it depends. Like there is no one answer. So I think it's not like there's one model which works the best for everything. It totally depends on the kind of data you have, the kind of problem you're solving, the kind of language you're doing. So it all depends on that. But yeah, you can definitely like there is research which like has shown that it helps to some extent. Okay. Next, we have do you prefer academic research versus the corporate world labs? That is something I don't have a concrete answer on, but I can tell you the advantages of both. So, basically, academic research is preferable in the sense that it has no restrictions. You have all the freedom you want. You can work on literally anything, and you won't be like asked to not do it. So academic research is much more free. You're not restricted by any corporate licensing or anything. So that way, I think I really, really enjoy the academia setting. The second aspect of corporate world, like research labs, the main advantage there is because these labs are so closely aligned with a company that you get to also see the effect of your research in a tangible application. So I guess if you are more interested in like seeing okay whether my research is helping a particular tool or helping particular people, then having a close collaboration with an industry lab will definitely be like more fulfilling. But that being said, yeah, I think I don't have a preference as of now because I kind of want both of like best of both. So it's yeah, I guess that would be my answer for that. Did you choose thesis in undergrad? Yes, I think that was sort of mandatory for us. Like we had to do a semester long thesis project, and I think I did that in I forgot. I think I did that in compilers. So yeah, but Yeah, I didn't take it very seriously then because, yeah, I think it was a last semester, but I highly encourage you to not do that mistake because I think that is a very good opportunity. Like you have a good like you have good 3 to 4 months to do like interesting research work. So you can like do a thesis in your, like you can do thesis in bits, but you can also do thesis outside of bits. So like explore whatever opportunities you get and do make good use of that time because you won't get such a good amount of time to do research later. um, how to tap into the alumni network for AI ML for advice. Okay. So I think so there are like multiple ways. One is that let's say you're interested in NLP. So you can like let's say visit CMU. Like most of the universities have websites where they also list this kind of students that they're doing. Most students have a website, so you can just directly reach out to the students via an email, and that's one way you can get in touch with. I think Bits also has this Bits MS to PhD. I don't know, it's a Facebook group or I think Excel sheet, which basically has information on what are the alumni, like what kind of programs they pursued. That is one way. And yeah, I think the most effective way I found was to like just go to university websites, and that has a lot of information, and you can like simply email any student you find who's doing interesting work, and most of the time if you send a very reasonable email they are quite responsive. How to select feasible opportunities for off-campus thesis. I think again, it all starts with talking to people. So you can find seniors who have like gone through that same process. Like you can just try to reach out to them, like understand how they got this opportunity, how their experience has been so far. And I think to know these opportunities first, you have to also like be proactive. So a lot of the times, so just keep on checking websites, keep on looking at advertisements, and yeah, and also I think especially for research, when you're trying to evaluate whether the particular professor or a particular institute is doing good research, check out their publications. Most publications are available online publicly, so you can like take a look at the recent most publications in Google Scholar and like try to get a sense of what a professor is working on in the past 2 years. So that is like the most easiest way to check and how like what kind of research they're doing and is it exciting to you. How to get into labs like MSR or IBM research after undergrad. So I think they might have an application process. So I'm not exactly sure as to how it works now because it has been so long. But you can just quickly check in with some people who have done that, or maybe just like check out the MSR website. And my guess is that they probably have like a formal application process. And if you don't find any information online, like again, like all of these labs have people listed like who are doing research there. Simply email one of them and ask them for more information, and I'm sure they'll be happy to provide you. So just like be proactive, like look for information, but if you don't find that easily available, simply reach out to them. Could you share your cold mailing for research experience? So so by cold mailing, what I mean is that you basically like a more effective email would be that you have a nice subject which is informative as to like maybe you're looking for, let's say, information on summer internships or information on research opportunities, and then in the email you basically write few sentences about what has been your experience so far. That okay, maybe you are a graduate, you're a computer science undergrad from so and so college, and you have been doing so and so work, and but focus more, like do your homework on the professor you're emailing. Like tell them, okay, that I read so and so paper of yours, I found it to be quite interesting, and if you like, if you have read the paper, then possibly you might have some more questions or possibly even research ideas. So you can just write that in the email that okay, I read your paper and I found this part to be quite interesting, or maybe I think this could also be extended. So you can also like mention that okay, what are the ideas which you thought could be extended into. That would be like a more informative email, and that also shows that you have done your research and that you're seriously interested in like pursuing this opportunity. That is what I mean by like having an informative email. Like don't just send them an email, okay, hi, I'm interested, I want to research internship. That is a very bad email and you want a response. Can raw research experience and publications compensate a profile for not being from a CS discipline? Yes, definitely. So people like universities highly encourage people to come from diverse backgrounds. So you can like tap into like interdisciplinary areas. So even if you are not from a CS background, you can like get some research experience, and maybe you can like do compensatory courses to get some more information.
I think the questions have been answered, all of them.
Okay.
So yeah, thank you,
Mhm.
ma'am, for taking out your time, and it was really an insightful talk. I'm sure people benefited a lot from it. So, like, if you be comfortable, I think we can move to the tables where if people have some other queries, they can ask you personally.
Okay, sure. So I'll just be back in like 2 minutes.
All right.